So I thought today we'd be talking a little bit about the relationship between gravity and quantum mechanics. Now, we believe, of course, that the fundamental laws of nature are given by quantum mechanics, right? At the microscopic level, we think that all forces in nature, perhaps including gravity, are described by the fundamental laws of quantum mechanics. And as a result of that, if you look at a field like the electromagnetic field, the classical description of the electromagnetic field is in terms of some sort of quantum mechanical average, right? So at the microscopic level, it is characteristic of quantum mechanics that you have, first of all, that the fields fluctuate. Right? Anything fluctuates in quantum mechanics, the position of a particle, the momentum, but of course the field as well. And we know that the field description is the correct fundamental description in quantum mechanics for the particles we know about, right? And the fluctuation is of order h bar, right? And the second, of course, essential component is that we have field quanta. Right? Field quanta. And so those are some of the key ingredients, right, of a quantum mechanical description, whereas the classical description arises as we take some suitable averages and we look over at long-distance behavior. So now, of course, usually we tend to think and say that quantum mechanics only applies to the very microscopic, short-distance, small-scale behavior. But of course, if you think about it a little bit, that's not quite true, right? Because we do know that there are quantum mechanical phenomena that extend over microscopic domains, right? So for example, a superfluid is an example of a quantum mechanical behavior that is macroscopic. A superconductor, neutron star, right? So nowadays we know that there are cases where you can have macroscopic quantum mechanical behavior. So the statement that somehow quantum mechanics only applies to the very smallest scale is in fact not quite true, because there are counterexamples to that, right? So now when we take an introductory quantum mechanics class, right, we are confronted with the basic laws of quantum mechanics, and the basic laws of quantum mechanics is that you have a Hamiltonian, right, which depends on P and Q, right, which is a certain operator that you construct out of the classical Lagrangian and the classical Hamiltonian. You get this object, right? And then the essence of quantum mechanics is that the commutation relation between the Q and the P is equal to IH bar, right? And so all of a sudden these quantities become operators that don't commute, and from that you get things like the Heisenberg uncertainty relations. Now another key ingredient of the introductory quantum mechanics for, say, a non-relativistic system is the fact that you have a wave function, right, or a state vector that is describing the state of the system at time t. And this Hamiltonian comes in a very special role because it determines the time evolution, right, the time evolution of the state vector, right? So you can, at zero, right? So you can write the state vector at time t in terms of the time evolution through the Hamiltonian operator at time zero, right? So if you look at this expression, of course, you immediately realize that this kind of formulation, that is, as I said, the basic one that we introduce at the very beginning when we talk about quantum mechanics, is tied with a definition of the time, right? Because the time plays a special role from the very beginning. The time arises because we are talking about the momenta which satisfy these commutation relations, and the momentas are essentially the q dots, right? So the derivative is a coordinate with respect to the time, and so the time plays a special role from the beginning. Now, if we are talking about fields, right, then we have basically the same kind of situation, right? If we follow that approach, then again we're going to have time evolution operators of fields, and in this case we again will have to introduce a concept of some sort of time, right, which is tied to a specific coordinate system that tells us how these fields evolve in time, right? So the canonical formulation, whether it is for particles or it is for field, requires the introduction generally of a time And that is a specific choice of coordinate system already in special relativity, right? And we understand, based on all the things that we talked about in this class, that that is something that is somewhat undesirable when you look at the quantum theory, because we understand now that, of course, the time is tied to a specific coordinate system, right? And in general relativity, there's different coordinate systems associated with different observers, which could be even in an accelerated motion with respect to each other. And so somehow this notion that you now, to define quantum mechanics, you introduce some sort of time is undesirable and not particularly appealing, right? So that suggests that in order to go about and describe the basic aspects of quantum mechanics, we should resort to some sort of other approach that does not require the introduction of time, and therefore, in a sense, is satisfying in a more better way the requirement that the theory be generally covariant. And so that is, of course, already for a single particle. That approach was developed a long time ago by Feynman. It's called the Feynman path integral approach. Right? So the idea of the Feynman path integral approach is that you write the amplitude, right? We talk about this in the quantum mechanics class, right? The amplitude for the particle to go from point 1 to point 2 is going to be a sum over all paths that go from 1 to 2 of e to the I over h bar times the action that is associated with the path, right? So in Feynman's formulation, you actually do not have Q's and P's, right? Instead, you rely on the action to tell you how quantum mechanical amplitudes are calculated, right? And so the picture that we have in this case is that you have point 1 and point 2, and the prescription is that you look at all paths that connect point 1 and point 2, and you sum over all of them, and that is precisely equivalent to calculating the same quantity within the canonical formulation, right, using P's and Q's, right? And so the ingredient, of course, in this theory, as I said, is the action, right? And if you have just a single particle, that is, of course, the integral of the Lagrangian, right? So integral in dt of L of Q and Q dot, right? And, well, that quantity, of course, is a number, right? Because you're integrating over the time, and so it's a quantity that is invariant. And in fact, we have seen that even in general relativity, this carries over because the trajectory of a single particle is described by an extremum of the proper time, right? You can get the equation of free fall by just extremizing the proper time for a particle, right? So in particular, you recover classical mechanics in this context by looking at the limit of h bar going to 0, right? Because when h bar goes to 0, you do a stationary phase approximation on the exponent, and that means that you look at ds equal to 0. And ds equal to 0, the variation of the action gives you the Euler-Lagrange's equation, right? So this is already known, of course, in classical mechanics, that is a good way of obtaining the equations of motion. And in the Feynman path integral approach, this is actually very clear and intuitive how you get this classical limit, because you have the action appearing explicitly, right? So that will suggest that you try to use this kind of methods also in the case of other theories. And of course, the first case that comes to mind is electromagnetism, right? And so you can develop this for electromagnetism as well. And the first thing you need to introduce is the action for electromagnetism. Right? So in that case, the action will depend on, well, all the variables that you have in this problem, which in the case of classical mechanics is just the q and the q dots, right? And it could be one q and one q dot, or it could be n of them if you have n degrees of freedom. If you have a field, then, well, you have infinitely many degrees of freedom. But in electrodynamics, of course, we know that you get Maxwell's equation. This is something that we discussed in this class, as well in some of the other classes, by just taking -1/4 the integral in d4x of f mu nu of x times f mu nu of x, right? Plus, well, we might, of course, have matter fields as well, which would be described by other fields which are not the A mu, right? Where f mu nu is the field strength tensor. And so that works very well, and it is one way by which you can, in fact, quantize electromagnetism using the path integral approach and get the usual results without ever introducing really operators and commutation relations and things of that sort. And this method, so the Feynman path integral method, is the method of choice, for other interactions that we encounter in nature, namely for so-called Young-Mills theories, which include quantum chromodynamics, right? The theory of the strong interactions, where you have a theory that is modeled somewhat after electromagnetism, but instead of having just one electromagnetic field, it has 8 of them, which are called gluons, right? And so it's a theory that has some sort of self-interaction, and in that case, the method of choice for quantizing it is, in fact, the Feynman path integral approach, which in particular leads to one essential key ingredient in doing the quantization correctly, which is the Fadeev-Popov determinant, right? So you'll learn about that in a quantum field theory class. And the other case is the electroweak theory, right? So-called Glashow-Weinberg-Salam model, which is also a non-abelian Young-Mills theory, where you also have this issue of doing the quantization correctly and having the correct Feynman rules, which is something that we derive using the path integral approach. So it is the method of choice for all, well, certainly for a number of theories that we know describe particle interactions in this universe. And so it does make sense to apply this to gravity, right? And so that means that we are dealing, instead of just a Q, right, we're dealing with a field that has infinitely many degrees of freedom. So our sum over paths, right, here, essentially the sum over paths is an integral over all functions Q, right? This is one Q of t. This is another one. We're supposed to sum over all of them, so it's some sort of functional integral. And so in electromagnetism, what we want to do is sum over all electromagnetic fields, all possible field configurations, which means we sum over all possible field configuration with e to the I over h bar times the action of the electromagnetic field, which is what I just wrote above there. And this is the Feynman path integral for electromagnetism, right? So given this preamble, we can now start to think about how this would work for gravity. Right, so apply to gravity. And so again, the key point, which I repeat here, is to enforce general covariance. So maintain general covariance at all stages. Right? So one could introduce a time, one could define a Hamiltonian, right? But in my opinion, the preferred method is to actually do things in a manifestly covariant way, where you preserve the fundamental symmetry of GR. And so that would mean that now you want to sum over all possible paths, which in this case is the sum over all metrics in some way, right? And so that means that the first ingredient you need is, of course, the action. Right? The first ingredient you need is the action, because that is the weighting factor in this Feynman path integral. And well, we don't have to do a whole lot of work, because in fact we discussed in this class that the action for gravitation is unique. The action for gravitation is unique, and so that is going to be minus 1 over 16 pi g. It's conventional to put this factor here in front, times the integral in d4x, times the square root of g, this determinant factor, times r. And perhaps there is a cosmological constant terms here as well, right? And plus matter fields, right? Which of course would be additional fields on top of the G mu nu that we have to start with. So most of the time, for now, we're just going to be concerned with pure gravity, right? And so the action is this Einstein-Hilbert action, and so we know that already. We don't have to reinvent that part, right? And so what we need to calculate now is an integral over all geometries, right? According to Feynman, you have to do an integration over all metrics of e to the I over h bar times the the action that is associated with this G mu nu, provided we do, again, just pure gravity and forget about the matter fields for a moment, right? And so that is our Feynman path integral in a kind of a picture book description. And so this measure is in fact known and is called the DeWitt measure. The DeWitt measure actually is a functional measure that was written down some years ago by Bryce DeWitt and tells us exactly how this integration is supposed to be done. It's a local functional measure, so it's just a product basically over all x's of dg mu nu of x. So what does this path integral tell us? Well, the non-relativistic path integral tells us what is the probability amplitude for a particle that starts here to end up there. Right, that is the quantum mechanical amplitude that appears in the Feynman path integral. And so here we have, in fact, a similar interpretation, namely this path integral will tell us, if we specify a little bit here the boundary conditions, will tell us what is the probability amplitude that if you start with a metric that is G1 on some surface, which we describe as S1, what is the probability amplitude that we end up with another metric, which is G2 on a surface, which is S2. So it will tell us exactly the counterpart of the kind of thing that we wrote down for a single particle, namely the probability amplitude for geometries to evolve, for metrics to evolve from one hypersurface to another. Right? And this formulation is what is basically referred to as the Hartle-Hawking path integral. Hartle-Hawking path integral. Right? So the application of the Feynman path integral method to gravity was developed originally by, well, of course, Feynman himself was very much interested in this issue, and DeWitt contributed in an important way. But I think later on, Hartle and Jim Hartle and Steve Hawking gave important contributions on what exactly the issues might be in defining something like this, and how you would go about and calculate it and so forth, and things like that. What they also suggested is the following, right, which is a bit of a technical point. But they did suggest that, in fact, it might be useful for practical purposes to do something that we do in quantum field theory all the time, and that is to do a Wick rotation. Right? To do a Wick rotation, and that is to define T is equal to minus I tau. And in the general relativistic context, that means that we consider complex space-time. Complex space-time, and that does have some very significant advantages. One advantage is that it improves the convergence properties of these integrals, right? You might worry that these integrals would have to be well, a certain prescription would have to be given on how exactly to do this integral so that it is convergent. And that problem usually kind of goes away when you do this Euclidean rotation, because then things become much more well behaved. And that is, of course, as I said, something that we do in quantum field theory all the time, to do this Wick rotation. And it is something that, if you wish, we also do in introductory quantum mechanics, where a number of times we do, for example, the adiabatic approximation, where we turn things on slowly or turn them off, and that ensures that certain expressions are well defined because of this adiabatic switching on and switching off is also an ingredient, an essential ingredient of time-dependent perturbation theory via the so-called Gelman law formula. So anyhow, this is one interesting way to proceed. And of course, when you do that, then the signature, right, in this Hartle-Hawking formulation, the signature goes from what we had in this class, which was minus plus plus plus, goes into plus 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 plus, right? So we're basically going from kind of a Lorentzian signature to an Euclidean signature. And well, I think it depends a little bit on who you talk to, but it can be actually quite nice to have all the components to have the same signature. And so if you want to be proper, then you're going to what is referred to as a pseudo-Riemannian metric to a properly Riemannian metric, right? Where all four components of space and time are treated in the same way, right? And so, all right, so this was kind of a long preamble, right? It is my belief that the quantum theory of gravity is encoded in this expression, right? And you might say, well, why don't you just go and calculate it? Well, of course, we understand and we realize and appreciate very early on in quantum mechanics that anything that in classical mechanics can be solved in half a page, in quantum mechanics can turn into something that is quite a bit more complicated. And nevertheless, we do understand very well how to quantize electromagnetism and non-abelian gauge theories. Not only that, but we know that they work very well, right? We discussed in the other class the fact that the G-2 for the electron tells us that quantum field theory is accurate to 1 part in a billion, or something of that order, right? So why don't we just go about and calculate this integral? Well, first of all, it's a functional integral, so quantum field theory is tough. It's a lot of hard work. And the other problem is that in gravity, you might not get the right answer if you do the weak field expansion. If you do any sort of approximation or expansion here, you might be misled in what is actually happening. And if you want to calculate that integral exactly, well, then you might have to wait until the next millennium or something like that, right? So it is a nonlinear theory. It's a nonlinear theory. And the nonlinearities are actually what I think is making life very hard and is slowing down, I think, the theoretical physics community, that at least that part that has an interest in gravity quite a bit. I think there are people that believe that you could use perturbation theory. I don't think so, but anyhow, it is a tough problem, right? So anyhow, now we step back a little bit and we go back to what Feynman thought, right? So Feynman's idea, or Feynman's question, if you wish, was, you know, when he got interested in gravity, right, which was in the 60s, he said, let me assume that I don't know anything about gravity, but I know quantum mechanics. I know quantum mechanics, and I know that quantum mechanics tells me, right, so you can erase everything here. Quantum mechanics tells me that I have particles that have definite spin. Right? So let me assume for the moment that I'm kind of ignorant about general relativity, that I don't know of Einstein theory, right? But I do know that in quantum mechanics, right? And this is an exercise that we do in the quantum mechanics class to show that if you look at the angular momentum commutation relations, right, the irreducible representations of the angular momentum algebra give you values for the spins, which are either integer or half integer, right? And so, in particular, if you're looking at particles which have the potential of mediating long-range forces, which are there for bosons, you're essentially limited to s equals 0, 1, and 2, well, possibly other spins as well, right? Quantum mechanics tells you that this is all you can have, right? And then for, of course, as I said, for matter, for fermions, you can have also 1/2 and 3/2, which, right, at this point we don't consider. And so suppose then that you know this and you just want to write down a theory that describes a particle of a definite spin, right? And so for electromagnetism, we know that the particle has spin 1/2, right? It is described as a result by a field which has 4 components. Essentially a vector, right? A vector in 3-dimensional space would have 3, but, well, in this case, we're in 4-dimensional space, so it's got 4 components, right? And this particle has 0 mass, right? 0 mass because we're interested in particles that can mediate long-range forces, and that is only going to happen when the mass is 0, right? And it should be coupled to a conserved quantity, right? And so we have a conserved charge, which is the integral in d3x of the j0 of x, right? And so there's a conserved current here, right? And that conserved current is a vector, is a 4-vector, right? And that leads to just a single conserved quantity. Now, if we look at gravity, as we already discussed in a number of cases in this class, right, we don't have a single conserved quantity. We have 4 of them, which is the energy momentum tensor integrated, right, the integral in d3x of t mu naught, right, of x. So there's 4 conserved quantities, right? And if we have a theory where you have this conservation of energy and momentum, then you must have an energy momentum tensor which has to have, well, 10 independent components, right? It has to have there has to be a t mu nu, right? There has to be a t mu nu. And so that means that the field that couples to that has to have the same number of indices, right? Because in the end, we're going to have an equation, box times the field is equal to a source, right? So the indices for the number of possible components for the source is tied with the number of possible components for the field itself, right? So that means that we have to have a g mu nu that depends on x, and that tells us that the spin cannot be 1. The spin cannot be 1, has to be 2. Spin 1 would never work, by the way, for another reason, namely spin 1 will immediately tell us that you have that opposite charges attract and equal sign charges will repel, right? And that is not a feature of gravity, right? That will not work. It's clear that it cannot describe gravity. And in fact, you can also have spin 0, and that works even less, right? Spin 0 is not a candidate for a theory of gravity because it just will not incorporate this feature, right? So that is the starting point, if you want, of Feynman's considerations on how you would then go about trying to construct a theory of gravity. So now let me do a warm-up. And let me show you how that works for electromagnetism. Because in fact, from the requirement that the electromagnetic field has spin 1, I can derive Maxwell's theory, right? And the idea is that you first try to write down a Lagrangian, right? A Lagrangian which depends on some fields, and we have to have spin 1, right, so that these things work correctly, right? And so when we try to construct this object, right, which is going to turn out to be minus a quarter f mu nu squared, right, then we can write down a number of terms. So if we have 0 derivatives, right, and if we have a field, right, which is this a mu of x, then with 0 derivatives, what kind of terms can we write down? Well, we want this thing to be a coordinate scalar, right? So one possibility is that we take a squared. A squared has no derivative. You're dotting a 4-vector into 4-vector, so that's a scalar. That will work too, right? That will work nicely. The other possibility is that if you have a current, then of course that will also work, and that contains no derivatives either, at least of the electromagnetic field, right? Then what about if we have one derivative? Well, if you have one derivative, then of course you have the d mu, right? And you have the a mu, and that will work as a term in the action, right? Except that it is not bounded. It can become arbitrarily positive and negative, and so it doesn't work because of the unboundedness problem. You cannot, unless of course you take the magnitude of that, but that's not just a monomial in the field. So then we have 2 derivatives. And when you have 2 derivatives, there's a number of different possibilities that you can have because at that point you can have either d mu a mu, and you can square it, right? And that would work, right? Or you can have d mu a nu, and then d mu a nu. You can have that term there, right? Actually, sorry, I want to have it this way. And this way, d mu a nu. And this term actually is the same as this one when we integrate by parts. Remember, the Lagrangian is inserted into an integral. And so what you can do is you can integrate this by parts, and it acts on the a nu, and you can have this d mu integrate by parts and acts on this one. So actually, this term we don't need to consider. But yet there is another term, which is, of course, the term that you have d mu a nu, and it's the one I wrote a second ago, times d mu a nu, this one, which is a new term, right? And so that's it. That's all you can have, right? Which means that now your action or your Lagrangian density, right, L, is equal to minus a constant, and that constant will turn out to be correctly 1/2 minus a half. And then you have d mu a nu times d mu a nu, which is one term, and plus alpha d mu a mu d nu a nu. And then, of course, you can have this first term, right? So we can have that beta a mu, right? But we want the mass to be 0. This is a mass term, right? And so that gives beta equal to 0. Beta is equal to 0. And now we can look at the Euler-Lagrange equations for this, right? Which means we vary this action with respect to the field a mu. And the Euler-Lagrange equations are minus d mu times d mu times a nu for the first term. For the second term, it's minus alpha times d mu a nu is equal to, if we have a source term, this is equal to, actually I want this to be a mu, and this is equal to minus g nu, like that, lower index nu, like that. So d mu d a nu minus alpha d mu a mu is equal to 0, right? So that's the equations of motion. And now what? Well, now we take the divergence of this, and we use the fact that the divergence of the current, is equal to 0. So we require that the current be conserved, right? And so that means that the divergence of this side has to be 0. So that tells us that d nu times d dot a, or let me write it this way, d nu times everything that we had above there is equal to 0, right? And so the first term gives us the minus del square of d dot a, and the second term gives us minus alpha del square d dot a, and that has to be equal to 0, right? Because those two terms give the del square, or a box, and this one gives d dot a, and this, of course, is also the box, so the del squared. So that means that alpha is equal to minus 1. Alpha is equal to minus 1. So that means that, first of all, this term is gone. That term is gone, right? And this one is minus 1. Minus 1. And this is, in fact, exactly the same as minus a quarter f mu nu. F mu nu, if you write f mu nu as d mu a nu minus d nu a mu. It's exactly the same. So that's Maxwell's theory. That's Maxwell's theory. So you can derive Maxwell's theory, right, to repeat. You can derive Maxwell's theory in half a page by requiring that you have a vector field, A mu, and that you require that the Lagrangian only contains 0, 1, or 2 derivatives. Then it's unique for a particle of zero mass coupled to a conserved current. It is unique, right? And so that's a warm-up. So there are no 10 different theories of a spin 1 massless particle. There's only one. It's Maxwell's theory, the one in Jackson, right? Maxwell's theory is unique, right? So Feynman's argument was that the same thing perhaps happens with gravity, right? So repeat for gravity. Repeat for gravity. Repeat for gravity, right? The question is, if you do require, right, the requirement again is that you start out with a particle that has spin 2. It is massless, and the energy momentum tensor is conserved. It couples to a conserved quantity. What do you get, right? So, now, let me show you, in the case of electromagnetism, let me do another little preamble, which is that in the case of, so this is this del squared, right? That box A mu is equal to minus J mu, right? And so we can actually invert this relationship, right? Because we can write that A mu is equal to minus 1 over k squared. If we go to Fourier space, is minus 1 over k squared times J mu, right? And so if we look at the interaction term, remember, is J mu A mu. That's what the interaction term looks like. And so we can stick the A mu in here, right? And so that becomes minus J prime mu 1 over k squared and J mu, right? Because we can eliminate the electromagnetic field via the fact that it satisfies this wave equation, right? And so if we have a coupling between one current and another current, so this is J mu and this is J prime mu, then that coupling is given by this factor 1 over k squared, at least for the choice of the Lorentz gauge. So that means that if we look at the static limit, right, then in the static limit, k squared is equal to k naught squared minus k vector squared, and I'm using here Feynman's signature, which is the opposite of what we use in this class. Feynman uses the signature which is plus, minus, 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 so we have different k's. So this becomes just say J prime naught times J naught divided by k squared, and so if you Fourier transform this, this becomes some density, right, which is we can just write that as a charge divided by 4 pi times the Fourier transform 1 over k squared, which is 1 over r, and then at t equal t prime, so at an instantaneous potential. So basically from this simple argument you can see that this particle gives rise to a 1 over r potential, and so something like that should happen also for gravity, right? We expect for gravity to have a kind of a similar structure, because if we have a spin 2 field, right, then we would expect that h mu nu is equal to 1 over k squared times the t mu nu. Right? That would be the analog of this, right? And in fact, we have seen that that happens in the Einstein theory in the weak field limit, right? And then the interaction is t prime mu nu times well, it's T prime mu nu times the H mu nu, right? And so that would become a T prime mu nu times 1 over k squared times T mu nu, right? Something of that type. And the static limit, this goes again into a 1 over r potential, right? So there is some similarity if we look at it at least from the most basic point of view, that there is a gravitational field and that it is related through some sort of a wave equation through to the sources, right? And so one key ingredient is, though, that this T mu nu should be conserved, right? That is the analog of what we have in electromagnetism, right? So now we want to construct the Lagrangian or the action. Right. So we want to construct the action, right? This S of G mu nu, which in this case we're going to call this the H mu nu field for now. It will turn out to be just the weak field expansion of the metric, right? And so we are looking for some Lagrangian which depends on the G mu nu, for some Lagrangian density which depends on the G mu nu, where the action is then the integral in what I call S, right? The action S is some integral in d4x of this Lagrangian of the G mu nu of x, right? And so we proceed in the same way as we did before, which is various terms that we can have, right? And it gets more complicated because now the field has a number of indices. And so to construct something that is a coordinate scalar, you can do all sorts of different contractions, right? So the first terms we consider is where the tensor indices are different from the derivative indices. So for example, we can take d sigma times H mu nu, right? And now we want to have, by the way, terms that are contain no derivatives. Those would be like mass terms. In fact, there's also a cosmological constant term that would work, but we're going to leave those out. We're just going to look at terms which have one derivative while they're unbounded again, so there's going to be none. So we're basically, for now, just restricted to terms that have only two derivatives. So if we write something like this, of course, that has three indices, and they have to be contracted with something. And so we have to have d sigma times H mu nu, right? And so that would work. That would work, right? Now, that's just one of many, because the other thing that we can have is we can have d sigma times d sigma H mu nu, right, times d nu times H mu sigma. So you see now that in the second case, the index sigma is not contracted with the other derivative, but this was contracted with one of the indices of the metric, right? Well, it turns out that actually this term is related when you integrate by parts to some of the other terms that we're going to write down in a moment, and so we actually don't need to consider that. So let's keep on going, though, and write the other terms as well. So term number 3 is going to be d nu times H mu nu times d sigma times H sigma mu. This is also allowed and is different from what we had a moment ago. And then the other possibility is that you have d nu times H mu nu times d mu. And now the two indices on the H are contracted with each other so that you have d mu H sigma sigma. Like that. That's another term you can have. And then number 5 is d mu H nu nu. So again, now in the first term, the two indices on the metric are contracted with each other, and then times d mu times H sigma sigma. And so now on both terms, two indices on the metric are contracted together, and then the derivatives are dotted into each other, which means that the second is upstairs, right? And so, well, that's all you can write down. And this term, as I said, is related to the other ones by partial integration. And so we don't need to write that down. Okay, so that means that now I, right, the action, what we called S before, is the integral in d4x. And so now we're going to add up all these terms together, right? And well, we don't know what the coefficients should be, so we're going to add them up together with different coefficients. So we are going to have a coefficient A times this first term here, right? So start with term number 1. So that is the sigma of h mu nu times the sigma times h mu nu plus b. So now we come to this term that also will have an arbitrary coefficient in front. So that is going to have a d nu times h mu nu times d sigma times h sigma mu. Right? And then we keep on going. Coefficient c is going to have this term here, right? So c times d nu h mu nu times d mu times h sigma sigma. Okay, and plus the last term, right? Term number 5. So plus d, some other coefficient, times d mu, and the trace, so h nu nu, and then d mu again, and then h sigma sigma, right? And well, that would be it as far as the gravitational field part is concerned, except that we also want to add the source term, right, which is the J mu, A mu for electromagnetism, right? And here we add the analog of that. And so that is a term that involves the T mu nu, right? So we're going to write that as minus lambda T mu nu times H mu nu, right? So this is our J dot A for gravity. And then close parenthesis, close parenthesis. Now, of course, that looks horrible, right? Because we have, well, it's the nature of gravity that we have all these indices. So we got to write down all the possible components and all the possible terms you can have, and that's the way it is, right? And so we end up with something that is rather complicated because we have we have 4 unknown coefficients, A, B, C, and D, plus the lambda, right? So the question is that of course Feynman asked is, can you actually constrain all these coefficients so that you get a number out of them, or do you have all these various parameters that you don't know what to take for them, right? And so the next step is to look at the equations of motion, which means you vary I of g mu nu, right, with respect to, well, our h, sorry, it's h, with respect to this h mu nu, right? So you vary this and you get an equation of motion, and that's a little bit of an exercise in doing this variation carefully. And so we get well, of course we get lots of terms again because we have many terms to start with. So we get a times 2 times, so one term is just the box squared. The box squared, right? So box squared is d mu, right? And so we can see where this box term, for example, is coming from. Right here you have these two indices which are the same. You can integrate this by parts and you can get the box squared, right? So you get the box squared a mu nu, and then you get the terms which are proportional to b, which are of delta beta times d sigma times h alpha sigma plus plus d alpha d sigma times h beta sigma. And so that's the B term. Right? The free indices here are alpha and beta, by the way. I use alpha and beta because it's easier to keep track of those and distinguish them from the other indices we have. So we have alpha, beta, right? And plus the remaining terms. So there's a term which is proportional to C, which is d alpha, d beta times h sigma sigma, so the trace of h, right? Plus another one that we can write as eta alpha beta times something, in this case d mu d nu h mu nu, and that's the C term. And then plus d times, so this is the term that is coming from this last term over here, right? So that involves the trace, and we get d times 2 times 8 alpha beta times del squared h sigma sigma. And well, that's it, except now we have the source term, right? And the source term, we're going to bring it over on the other side. The variation with respect to t mu nu, h mu nu just gives us lambda t mu nu. So this is just equal to, we can write this as minus lambda t alpha beta. I think I reversed the sign everywhere. Did I? So now we look at the divergence condition. So remember, in electromagnetism, right? You have that d mu j mu is equal to 0, right? And that provides a consistency condition. And in this case, we're going to do the same. We're going to multiply everything by d alpha, right? D alpha of everything. And we use the fact that on this side, right, d alpha t alpha beta is equal to 0, right? So that means the divergence of all this mess is going to be equal to 0, right? So let me take out that bracket. Let me not confuse it. So we take the divergence, and the divergence is that we get 2a times d beta times del squared times h alpha beta plus b times d sigma times del squared h alpha sigma plus the terms which are, these terms have the same structure. You see they both have a del squared. That's why I wrote them on the first line, even though they have different coefficients. And the second set of terms are d beta times d sigma times d alpha times h beta sigma plus c times d alpha del squared times h sigma sigma. And they also have the similar structure. Actually, they don't. Sorry. They don't. So plus c, we'll look at those in a moment, plus c d alpha times d mu d nu times h mu nu plus 2d times d alpha del squared times h sigma sigma. And this is supposed to be 0 because the divergence on the right-hand side is equal to 0. So we recognize that some terms are the same. They have the same structure. So these two terms have the same structure because they involve the del squared. You can see that beta is summed over in this case, and the sigma is summed over. But those are just dummy summation indices, so we can call them anything we want. And these two terms also have the same structure. You see that they're exactly the same, d alpha times del squared, d alpha times del squared times the trace, right? So because they have a different structure, they each one have to be individually equal to 0, which means their coefficients have to be equal to 0, right? So that provides finally a constraint on the A, B, and C's and D's, right? So we have that 2A plus B that multiplies d beta del squared times h alpha beta is equal to 0, which is this one. Right? So we write the overall coefficient as 2A plus B times this. That has to be 0 because that term is different from the other ones. Right? And then similarly for the second set of terms, which is that B plus C times d beta and then d sigma d alpha h beta sigma, that also should be equal to 0. That also should be equal to 0. And finally, C plus 2D of d alpha times del squared times the trace h sigma sigma is equal to 0. All right, very good. So that tells us immediately that there has to be a certain relationship. And so first of all, we take an overall factor in the action out and define A to be equal to 1/2. So we set A equal to 1/2. And because we can rescale the whole action by a coefficient, and that just redefines the lambda as well. So we're going to call the lambda that is normalized by the same name. So anyhow, we can take the A to be equal to 1/2. And then it follows that B is equal to -1 to allow for this first relationship to be satisfied, right, for arbitrary choices of the fields. B equal -1, C is equal to 1, and D is equal to -1/2. Okay, so that is actually a remarkable result because it shows that if you write down an action or Lagrangian which has just about all the terms you can think of, then by looking at equations of motion and requiring this kind of, it's essentially the Bianchi identity in this case, by requiring the divergence of the equation of motion be equal to 0, that fixes all these coefficients. It fixes all of them, all right, which is very nice, okay? So that means that we have now the correct action, we have the correct Lagrangian for a spin 2 particle, and we have the correct equations of motion, right? Now, as you remember, it is actually, we discussed this briefly already when we talked about the weak field expansion. It is convenient to define this h bar quantity, which is the trace reversed form of the metric, namely to define h bar mu nu is equal to h mu nu minus 1/2. In this case, we just have an expansion about flat space, so minus 1/2 h mu nu. This is just a flat metric times the trace, right, the trace. So, which we're going to write as h sigma sigma, but in fact, usually h sigma sigma is just denoted by h. It's even simpler like that. When you just have an h with no indices, just a trace. Okay, so that particular has the property. So the bar operation takes the mu nu and reverses the trace. So if you do it twice, h bar bar mu nu is actually equal to the original h mu nu. So anyhow, if you do it in this way and you look at equations of motions with all the A, B's, and C's that were given here, then we get, for the equations of motion, we get del squared h mu nu. Right? That was the first term I think we wrote down. And then minus 2. Remember the coefficient of this term was 2a. A is equal to 1/2, so 2 times A is 1, so we get a 1 here. And all the remaining stuff can actually be written in a simple way in terms of this h bar variable. So minus 2 d nu d sigma times h bar mu sigma. So there's a bar here. And we can also do the bar on the t mu nu. And so as a result, we can rewrite it with the bar in this way. And so that is the, if you want, the Euler-Lagrange equations. Right, so the Euler-Lagrange equations have this form with no coefficients anymore, right? So A, B, and C, and D are gone. The only thing that remains is, of course, the lambda, right? Because that cannot be fixed because we take the divergence of the equations of motion, and the divergence of the t mu nu is assumed to be 0, so that goes away. So these are the field equations that you derive from assuming that you have a particle of spin 2. And now you recognize by looking at this a little bit that it is in fact invariant. It is invariant under h mu nu goes into h prime mu nu is equal to h mu nu plus d mu chi nu plus d nu chi mu. So the above equation is in fact invariant under this transformation, which is the gauge transformation we already saw in the case of the weak field expansion. And of course here you get it again. So as a result of the fact that if you wish this particle has zero mass and is coupled to a conserved current, you have that the equations of motion are actually invariant under this transformation. Which means, what does it mean? It means that you can choose a gauge. Right? It means that now you have this freedom to choose a gauge. And of course, the gauge you choose is that this is equal to 0. Right? You choose a gauge in which you set all that stuff equal to 0. And that is a freedom that you do have. And so as a result of that, we just have that box, h mu nu, is equal to minus lambda t bar mu nu. So we're left with just that, right? And right, and so that allows us to conclude. That allows us to conclude that so that h mu nu, right? We can now Fourier transform this, and the Fourier transform of the box is minus k squared, right? So we have that h mu nu is equal to lambda over k squared times t mu nu with a bar, right? And so the original interaction term, which was lambda times h mu nu times t mu nu, can be written in terms of the t and the t bar. Right, so let me write that over on this side. So the interaction term so the original interaction term is, well, it becomes, remember it was a lambda, right? It was a lambda t mu nu times h mu nu. Right? That was the structure of the original interaction term. But I can write the h mu nu, I can write it as lambda over k squared times t bar mu nu. So there's two lambdas involved, so I get a lambda squared of t prime mu nu, right, times 1 over k squared, which is coming from there, and then times the t bar mu nu, right? And now I consider static sources. So if I consider static sources, then the only thing that survives in the t mu nu is the t naught naught, right? So the Tij's, they're proportional to velocities. We can set those to 0. So we have that then the T bar naught naught, which is going to enter there, is equal to the T naught naught minus 1/2 times the eta naught naught, which in this Feynman notation is 1, and then times the trace of T. And so that is equal to 1/2 times the T naught naught, right? And so this interaction becomes just lambda squared times the over 2 because of the 1/2 there, times the T naught naught prime times 1 over k squared for static interactions times T naught naught again, right? And there is a minus sign here because Feynman uses the signature, which I'm following his own, his choice of signature, and his is plus minus minus minus. So his k squared is equal to k naught squared minus k squared, which is the opposite of what we used before in this class. So anyhow, that's how you get this minus sign, right? And so the Fourier transform of this is going to be 4 pi times 1 over r, right? And so lambda squared over 2 is going to be 4 pi times g, because that's the Newton's constant that multiplies the 1 over r. So finally, that has allowed us to actually establish a relationship between the original lambda and Newton's constant. And interestingly enough, of course, the sign of the original lambda plays no role. Right? The original lambda could be positive or negative, but it doesn't matter. The interaction is always attractive because you just have a lambda squared appearing in it. Right? So that establishes a relationship between the original lambda and the Newton constant. Now, you might think that maybe, he said that this particle has spin 2, but it's not entirely clear maybe that it has spin 2. So maybe one should go about and actually prove that this particle is a particle that describes correctly gravity, which is a massless spin 2 particle with just 2 helicity states. So how would you go about proving that? Do we need to do any extra work? I don't think so, because we already analyzed this equation, didn't we? We already analyzed the equation box h mu nu some time ago under the assumption that you had this invariance, right? We went through that exercise, and what were we able to show? Well, to make life easy, we considered a plane wave, right? And the plane wave propagated in the z direction. And then we were able to show that the only 2 independent degrees of freedom were the polarizations associated with E1, 1 and E1, 2, right? That there were only 2 polarization states that you could not set to 0 by a choice of coordinates or a choice of gauge transformation, right? And we also showed that when you did a rotation, that particle behaved exactly like a particle of spin 2, right? Remember that phase factor, which was characteristic of a particle of spin 2. So we actually don't need to repeat that argument. I mean, Feynman does that in his lectures. He goes through a plane wave expansion and shows that it has spin 2. But we have done that exercise already, right? So this is essentially, so what is it at this stage? Well, it is essentially a derivation of Einstein's theory from what we would describe as quantum mechanics, right? Because we are starting out with a particle that is massless and has spin 2, right? Which is what quantum mechanics tells us. We are writing down the possible terms we can have in the object that is supposed to describe the behavior of this particle, which is the action, or the Lagrangian, right? And we see that under certain constraints, which is the fact that it couples to a conserved quantity, which is the energy momentum tensor, the action is unique. And so we're basically deriving or rederiving Einstein's theory from these assumptions, right? And so that is remarkable. Except it's not quite like that, is it? Because in fact, what we have derived at this stage, what he derived at this stage, is not the Einstein action, is it? or the Einstein field equations, which is the same thing, right? One or the other, they're just equivalent, right? What we have in fact derived is just the leading term in the weak field expansion, right? We just got the first term in the weak field expansion, which is the linearized theory, right? It's just a box h mu nu thing. It's exactly like what you get from Einstein's theory. It's non-trivial, right? It's highly non-trivial, but this is exactly the same form. There's no difference. The lambda is related to the g by that, so they're exactly identical, but this is just a weak field limit, right? And so now the next step is, of course, to show that when you go, to whatever the next step is, that you get all the additional terms that you get in the Einstein theory. How many additional terms do you get in the Einstein theory? Well, infinitely many. Infinitely many, because the Einstein theory is intrinsically nonlinear, right? The action is not a polynomial. It contains a square root of the metric. There's infinitely many terms. And so what we've just shown is the equivalence of the two when you look at the weak field limit, right? And so the next step that he addressed, that needs to be addressed, is what happens to higher order. Right, so what happens to higher order? Higher order. Well, it's not even obvious that there is a higher order. Why is there a higher order? I mean, maybe this is all there is to it. No, clearly this is not there is to it because of the following argument. Namely, we do have that there is a field equation associated with the H field. There is an action that is associated with that H field, which we don't want to rewrite again, but it has 4 terms, right? Well, the action, of course, is, right, the action or the Lagrangian, which is the same story, right, the integral of the Lagrangian density over all x, right? This Lagrangian is, right, normally it's viewed as being t minus v, right? It has a Lagrangian. You vary that, right? You construct the action and you vary the action and set that equal to 0, and you get that equations that are a Lagrange equation, right? Well, if there is an action, then there is an energy. Right? There is an energy because there is also an energy which is t plus v. So this thing, whatever we described, because it has an action, it has an energy, which means that this gravitational field carries energy and momentum. Now, that energy and momentum has to be put in, right, has to be put into the equations of motion, because if we write box h mu nu, right, and let's say that there is no matter, then the t mu nu is equal to 0 to start with, right? But even if there is no matter, we have to add to the right-hand side of the field equations the energy and momentum that is associated with the gravitational wave. So we have to add something that is the t mu nu of the H field. Right? So we need that. We need that. So just because this wave carries energy and momentum, there has to be a source term. Right? So what does that source term look like? Well, this requires a little bit of thought, right? But the source term is of the following form, right? You can work that out from the action, right? From S, from S, so the t minus lambda, so the lambda t mu nu, the lambda t mu nu of gravity is non-zero. And, well, it will have, so it's something, it's the analog of E squared plus B squared for the electromagnetic field, or whatever the energy momentum tensor is for an electromagnetic field. And so it is h d mu h lambda sigma times times d nu h lambda sigma again upstairs, plus a number of different terms, right? So this is the energy momentum tensor of the h mu nu. which is non-zero. Which is non-zero. Well, that, of course, has to be included in the action. Action. And what kind of terms will it give in the action? Well, anything that appears in the field equations, sorry, there has to be an H here. Anything that appears in the field equation, which is quadratic, will appear in the action as a term which is cubic, right? So this will give a cubic term in the action, right? And so that means that you need to add an extra piece to the action in order for this thing to be conserved, for this thing to be consistent, right? And now you can again work out the requirement that right-hand side, or sorry, I should say the left-hand side of the field equations be covariantly conserved, and that will tell you that this is a consistent theory, that you have to have overall energy and momentum conservation again, and this will work out provided you have this correct form for the energy momentum tensor that is associated with the gravitational field itself. And you will have to repeat this procedure several times, because as soon as you add the cubic terms to the action, the field equations are changed, the consistency conditions are changed, and you get an extra term in the energy momentum tensor for the gravitational field. So the process seems to never end, because as you add a term, you recognize that you have to add more terms, and it goes on, and it's an infinite process. And at the end of the day, what Feynman and others after him who did it more properly, what they were able to show is that at the end of this process, the only theory you get through this iterative procedure of adding the energy momentum tensor to the gravitational field is actually Einstein's theory. And so you get Einstein's theory at the end. So at the end of the process, this is what you get. So we're pretty much at the end of the lecture. So to summarize, what Feynman was able to prove is that if you have a particle of zero mass and spin 2, then you can write out what the action will look like, and you get basically the weak field expansion to lowest order for the Einstein action. And that particle, that field, the Gravitons field, carries energy momentum, so you need to add more terms in order to make the theory consistent. And when you do that, when you do this iterative procedure, at the end of the day, you have infinitely many interaction terms, and the action is exactly the same as the one that Einstein wrote down, namely it is that square root of g times r. And so the conclusion is, right, of this argument is that if you believe that you are describing a particle of spin 2 and zero mass, then the only Lagrangian that describes that particle is the Einstein-Hilbert Lagrangian. And that is unique in the same way as the action for electromagnetism is unique. So just like Maxwell's equation is the only theory that describes a particle that has spin 1 and zero mass, in the same way, the action that Einstein and Hilbert wrote down is the only action you can write down for a particle that has zero mass and spin 2, provided, of course, you restrict yourselves to just two derivatives of the field, right? So that is very interesting in a number of ways. The first way is that it shows the uniqueness of the Einstein-Hilbert action, if you did not believe in it yet, right? And it shows it from a completely different perspective, right? Because before, the perspective we adopted was the principle of general covariance, right? That the physics described by different observers should be the same, that there should be a set of invariant equations that would describe the physics. And here, none of that comes in, right? You have it approached from a different angle, which is from the angle of quantum mechanics. The angle of quantum mechanics says that you only have certain spins, which for bosons are integers. And if you have a spin 2 particle, which is the only thing you should consider if you have a conserved energy and momentum tensor, then for that spin 2 particle there's a new unique action, which is this, right? So if you hear somebody saying that they have another theory for gravity, then you should be skeptical. I think you should be skeptical because there's this amazing result, right, that Feynman derived. And so you can read more about this, of course, in Feynman's book, right? The Feynman Lectures on Gravitation does precisely this argument at the very beginning. And I think it's fairly straightforward. Some people say, well, it's a little bit of quantum field theory, but it isn't. In the end, it's just looking at the action and its variation. And in any case, even if you were not able to follow all the details, you will be able to appreciate the message and how powerful this result is about uniqueness of physical theories and how little room there is, right, in modifying gravity. If somebody were to tell you that there is an experiment has been done where there are deviations from gravity on solar system scales, then you would be rather skeptical, right? I mean, there was, for a long time, there was this issue of the Pioneer anomaly, right? People thought that this Pioneer spacecraft that was basically escaping the solar system after many, many years it had traveled, there was some effect that would indicate that the laws of gravity were actually not correct and that there was some additional contribution to the gravitational potential, right? And, well, that is certainly possible because, the laws of physics ultimately, who knows what they are, right? We just have some, at this stage in 2014, we have some knowledge of what we think are the fundamental laws, but they are probably not the ultimate answer. But it is not easy to modify gravity. It is not easy to modify gravity. If you think that you have really a force that is based on a spin-2 particle, then it's a unique theory. And there's not really a whole lot you can do except adding a scalar, right? If you add a scalar, if you add another particle, then that could change things, right? A massless particle, it could be a scalar, it could, for that matter, could be, some other spin as well, then that could happen. But the spin-2 theory of a massless particle, that's not easy to modify in a consistent way. That you gotta give up some fundamental principle, either gauge invariance or general coordinate invariance. All right, so that's it for today's lecture and for the course as a whole. And if you have any questions, please.
If you
yes.
combine Dirac equation with general relativity, you get a spin 1/2 particle?
Absolutely, absolutely. You can add all the matter particles we know about. You can add electrons, neutrinos. You can add quarks. You can add, of course, the Higgs boson, right, as far as scalars. You can add W's and Z's. There is really no fundamental issues in adding those to general relativity. And there will be more T mu nu terms, right? The energy momentum tensor describing matter will contain all sorts of different terms. And they all have to be coupled in a way which is consistent with general covariance, right? So when you add, say, a scalar particle, right, you have to have derivatives combined with the G mu nu in the right way so that the resulting expression is generally covariant, right? And if you have a Dirac particle, or it could be a spin 3/2 particle, which is described by the Radiative-Schwinger equation, then you would have to do things the right way so that the resulting theory is generally covariant. Usually when you have fermions, you have to introduce a local Lorentz group, which means that you have to introduce what are called tetrads or Vierbinds. And so there's a little bit of a technical complication in doing that. But nevertheless, the underlying principle is still the principle of general covariance. That should apply to any form of matter, right? General covariance does not apply to the gravitational field only. It applies to everything else that couples to it, right? That, the laws of physics should be the same when described by different observers. That should not apply to gravity only, right? And so that, of course, leaves little room at the end. And so the question is, where is really room available, right? And room available is at the very top or at the very bottom. So things could change at extremely short distances, right? Where you could have something like string theory take over, right? Where you could have that the fundamental degrees of freedom maybe are not fields. Maybe they are, things that look like strings, and that, again, you would have to somehow formulate that theory again in agreement with the principle of general covariance, I think, but certainly the degrees of freedom would be different. And then things could change on very large scales as well, because then at that stage, there could be modifications of gravity that happens at extremely long distances. still in agreement with general covariance, but maybe, you know, some sort of non-local terms or things that somehow are related to Mach's principle, some scalar tensor theory and so forth. So there is room for changes, but not everywhere, right? They have to be consistent from, at least from a theoretical point of view, as opposed to a phenomenological one. From a theoretical perspective, I think these theories generally are very highly constrained because of the underlying principle, which ultimately might not be valid, right? I mean, it could be that on the scales of the universe as a whole, that, you know, you don't have the different observers describe exactly this physics, that there is a preferred frame and so forth. So deep questions, right? But here in this class, we try to answer the question of what do you know if you proceed from certain assumptions? That is, what statements can you make if you do assume that the equivalence principle is exact, if you do assume that you have exact general covariance? Then this is what comes out of it. And that derivation is unambiguous, right? Now, it could be that some of these principles in the end are not valid. I mean, we know that, you know, at some point Galilean invariance was replaced by Lorentz invariance, right? So things change over time. We have to have a sense of history even when we do physics and understand that things at some point will change and that we will gain a deeper understanding of how nature works. But nevertheless, within a certain set of assumptions, this is what you get. And it is fascinating, right, that the theory is so highly constrained that in many ways it's very hard to get anything else, right, unless you give up some very basic principle. Right? And yes?
Derivation didn't use the, I mean, in this Feynman's derivation, you didn't use the principle of gravity.
Right. Very good point, right? In Feynman's derivation of, if you want, general relativity from quantum mechanics, in quotes, right? He did not use the principle of equivalence. He did not use the principle of general covariance. He'd never talked about different observers, you know, that are in any state of motion with respect to each other describing the same physics. He did not use that. What did he use? Well, he used Lorentz invariance, of course, right? So Lorentz invariance in a flat background, right? So he starts out with, but his new ingredient, right, which is just as good, it seems, is that you have a massless spin 2 particle, right? And so which one is better or which one is more fundamental? Well, that is a matter, of course, of opinion. But again, coming back to the beginning of the lecture, Feynman's point was that we do believe that the underlying laws of the universe are quantum mechanical. He made this point. He said the theory of how matter is put together, we think, is not classical, it's quantum mechanical. And he said quantum mechanics tells us that we have particles of definite spin and definite mass. And if we take that seriously, then we should think of gravity in the same way. We should think that we have a graviton, which is spin 2. And if you do that, if you take that assumption, this is what you get. So it is a beautiful result. It is very deep and it is very interesting because of that. And I think it fits perfectly within the framework of this class to discuss that. You know, we're limited by time, so, you know, we did things rather quickly. But I do encourage you to pick up Feynman's book at any time because it, again, it reflects his originality. You know, he's trying to think about things in a completely different way, right, and from a different perspective, and it does shine new light on classical general relativity because of that. And yes?
You haven't mentioned anything about the singularity problem?
The singularity problems are still there, right? Feynman's approach still recovers in the end general relativity. General relativity tends to have horizons, tends to have singularities. If you look at these singularities in detail, right, we can debate this forever, but first of all, we discovered that in the case of the Schwarzschild black hole, you had this horizon, but one interesting aspect was that the horizon seemed to be there or not depending on the state of the observer.
Singularity is 0.
The singularity, if you look now at cosmological models, you have the singularity at t equal to 0, right? You have the Big Bang, so you run the movie backwards and you look where we are now and you see at what happens when you go to early time. There is a moment where there is, you know, very high density and the universe is very hot and compact. And gravity has a singularity, right? The scale factor seems to go to 0.
What about the R equals 0?
But, well, do you know what the laws of physics are going to be at r equal to 0? Because I don't. I don't, right? So at some point, I think, you have to be careful about extrapolating present laws of physics to a domain where they might not be ultimately valid, right? We are talking about a situation of ultra-dense matter, and what happens at that stage, we do have a very hot soup made out of all sorts of particles. Do you know what particles are in there? I don't. Maybe you do. I think there's certainly going to be quarks and leptons, right? And a lot of other stuff, and gluons, and maybe more that we don't know about. So we can extrapolate backwards based on the known laws of physics and the known understanding of nuclear physics and nucleosynthesis and all of that, and we can go a long way, right? But then at some point it becomes philosophical, right? Because at some point it would be foolish to assume that we know everything up to distances equals 0, right? And in fact, the point that that string theorists make, which is a very valid point, is that ultimately when you go to very short distances, then you will have, that maybe the fundamental equations are a little bit different. And that would have to be fed into the Einstein equations, right? Einstein's equation only tells you what happens if I give you a T mu nu. You have to tell me what this T mu nu is, and then you have the equations based on gravity. Remember also that when you go to very short distances, curvature squared effects become important, right? Remember there was those R square terms, and we dropped them. We said they're not important because they only are relevant when you look at distance scales which are comparable to the Planck length, right? Because then those derivatives get very large and the effects are important. So curvature squares term could be important at that stage. We don't know. And so as we extrapolate further back in time, at some point we leave the domain of physics and what we understand nowadays and start to drift a little bit, perhaps, into metaphysics, right? And that is, of course, always the danger. I mean, there's nothing wrong with it, but we have to understand that at some point we have to draw a boundary. I mean, I wish we understood everything that there is to understand about physical laws, but a little bit of a sense of history tells us that's probably unlikely, right? That when you go to very short distances, then there is going to be some unknown element. But the point of this course is to tell you to draw a boundary and say, well, there's a lot of things we don't know, we don't understand, but there are some things that we do understand very well, and we understand that if you assume this, then you get that. Right? If you assume that the principle of equivalence is correct, the general covariance is exact, then this is what you get. And that might not very well be the ultimate description of the universe, but it is a way by which we use the tools of mathematics to actually derive things, right? We don't wave around our hands, and we say, if you assume this, then the mathematics will lead you here, and this is what you get. This is the equation you will have, right?
It sort of has the feel of the ultraviolet catastrophe.
Huh?
It sort of has the feel of the ultraviolet catastrophe. Like classically it blows up, but then, in statistical mechanics.
Ultraviolet catastrophe, right, in the case of the Planck distribution, yes, right. At some point, then the laws of classical physics broke down and you had to introduce quantum, right? But of course, at this stage, the quantum is in there, right? The quantum is in there. I think we're more confident based on today's lecture that actually gravity is consistent with quantum mechanics as well, provided we know how to understand. We understand how to work out its consequences, which is a real challenge because the theory is nonlinear, right? But nevertheless, it doesn't look to me like there is any fundamental inconsistency between gravity and the laws of quantum mechanics. I would be very surprised if there was one. But whether there is, of course, some sort of ultraviolet catastrophe when you go to very short distances at t equal to 0, well, that's the issue of exactly what are the laws of physics when you go to distances which are comparable to the Planck length, which is, of course, 10 to the minus 33 centimeters, right? By the time you get to distances which are very small, then we don't know. In fact, we don't know what happens above a TeV, right? And a TeV corresponds to, some fraction of 10 to the minus 13 centimeters. And we don't know what happens at energies which are, or distance scales which are this small, right? Because we know, based on the theories we understand, the electroweak theory and quantum chromodynamics and so forth, we only understand what happens up to distances which are a fraction of a Fermi, right? And beyond that, there might be some very new marvelous physics that perhaps the LHC will discover. You know, in a few years or so, we might find that there are new forces. So we don't know. We don't know at that stage. So there's a lot of things that could happen and have happened in the past. Physicists have always been surprised. You know, there have been a lot of surprises during my physics career, right? Neutrino has a mass, and you know, there's a Higgs, and there's you know, indirect evidence for gravitational waves and all that kind of stuff. So there will be new discoveries, and those new discoveries eventually will change physics at very short distances. Most likely will, right? So ultimate theories, I don't know. I mean, people talk about a TOE, theory of everything, right? There might be such a thing, but maybe not. You know, we don't know. We'll see.
So you said the action for gravity is basically constrained. But, so I know there are people working on obviously like F of R.
Yes.
They're called what walk theories.
Yes.
It's like what? Like are they breaking?
No, they're not. Yes, well, they're breaking something, right? So yes, so the question that Aaron is asking is, what about these F of R theories, right? So we start out with action for gravity, right, which is say -1/16 pi g, right, times the integrand d4x times the square root of g times r, right, and then there's a lambda term as well, and people have worried and wondered whether there could be other terms. So F of R theories means that you now modify this in, well, you want to preserve general covariance, so it means that whatever appears in the action is going to be some sort of coordinate scalar, right? So this is a coordinate scalar, right? But it's not the only one, because you can have R squared, you can have R mu nu, right? And you can have R mu nu lambda sigma, R mu nu lambda sigma, right? And so forth. And you can have higher powers, and then you can bring in covariant derivatives, so you can have box R, right? There's also things which are of the type box R and maybe box R squared. So there's all sorts of things. And how did we avoid this kind of plague? Well, we avoided the kind of plague because we insisted that the action contain only up to second derivatives of the metric, which ruled out all these things because they contain 4 derivatives, right? 4 derivatives, right? And so the F of R people say you take this and you replace it by F of R, where F is a scalar function. And so typically this is just, say, R times 1 plus some coupling divided by maybe R squared, you know, something like that. And that's usually the kind of models you play with. And well, I'll let you decide whether you think that this is the appropriate way to go or not. It's certainly one way of modifying gravity, right? The question, of course, well, there are many questions, right? Why should it be, in fact, usually there's a power here, right? So this is R to the n, right? And then there's some coefficient there, right? And the reason why people thought that this could be attractive at some point is because if you have a 1 over R term, it tends to accelerate the expansion of the universe at later times. So it can mimic the cosmological constant term. So in these theories, you can get away with not having a vacuum energy and having instead this kind of term. And you will find thousands of papers on this. And of course, my question would be, why having this and why not having 1 over Riemann squared, for example? You know, you can have all sorts of things or any power, and anything that is a coordinate scalar, you can add it to it. The answer is usually, well, this is the simplest. Okay, well, it's the simplest, sure. But, you know, So I think people have considered modifications to gravity in the form of adding extra terms to the action, and they will continue to do so. There was some unhappiness about the cosmological constant being non-zero. I don't belong to the group that was unhappy because I always thought it was a natural part of general relativity and it should be there. And I think it's very natural to view it as a vacuum energy. Right, it's a vacuum energy, so the lambda can be viewed as some sort of expectation value, right? Expectation value of the curvature, right? In this form, right? This would be the 4 lambda. So in a quantum theory, it's natural to have non-zero vacuum expectation values. We have that for the Higgs field, right? The Higgs field has a non-vanishing expectation value. Why should gravity not have non-zero expectation values? And if the gravitational field does, then that's precisely the explanation for lambda. So I think, you know, there's prejudices, of course, of which way one should go, but yes, but in any case, this F(r) theory is consistent with general covariance, but it does not have just second derivatives of metric upstairs. It has them downstairs, right? There's a fraction, so it is a bit different because of that. And yeah, any other questions? All right, so I'll see you next week then at the presentations.